Okay guys, I released an N-channel Mosfet tutorial video, which I'm going to have to delete because I found out some new information which I'm going to share with you now. Okay, so basically it was the placement of this resistor. This is the correct placement before I put it right here. So it's supposed to be a resistor between the gate and the ground, not a resistor on the gate heading to the gate in series with the gate. That's the placement of a resistor when dealing with a NPN transistor, not an N-channel MOSFET. So I corrected that now. Let me just go through and make the tutorial again from the top. So, okay. First we have our plug, which goes into the AC wall outlet. This is our wall wart / AC/DC adapter. Here we have a lithium ion battery that we're looking to charge. So in this example we'll say this AC/DC adapter outputs 4.2 volts, and that's the maximum charge of this battery that we're trying to charge. So I'll put that, and then here we have our N-channel MOSFET as low side switch. So it's located here on the ground side of this circuit, the minus side. Okay, so power will pass through the positive side into the positive side of the battery, and then out the negative side of the battery, in through the MOSFET, and then back out and back into the AC/DC adapter / wall wart. Okay, so the leftmost pin of the MOSFET, which is here, is called the gate. The center pin is called the drain, and the right pin is called the source, which I labeled here. And then here we have our microcontroller. This is a drawing of Arduino, and right here is the ground, and then here is the digital input output pin. Okay, so in order to switch this MOSFET on and off, that's what this circuit's for. When this MOSFET is switched off, this positive going into the front of the battery, the positive side of the battery, and the negative coming out of the battery and going back to the negative of here, that circuit is broken when this is off. When this circuit is not broken, when this is on, because then it completes the circuit. Okay. Now, why would we want something like that? So that we could shut off charging once it's full. Or we could turn it on and off quickly in order to use the MOSFET as a variable resistor in order to reduce the total average current passing through the battery in order to throttle that. Okay, so here we have the digital output pin. When this goes to high, this goes to the gate pin of the MOSFET, turning it on, filling the internal capacitor of it, and connecting the source and drain pins so that it becomes on. Okay, now when this turns off, this pin goes to low, and then this switches off. Note that the source side pin, the far right pin, branches off. It forks. One fork goes to the negative of the wall wart, and one fork goes to the ground of the microcontroller. Ground negative black. That's because the microcontroller needs to share the ground in order to be able to send the high signal to turn on the MOSFET. They need to share a ground. Now, this is the weird part. This 10K ohm resistor shorts from ground to the GPIO output pin, and the purpose of that is to ensure that the GPIO output pin defaults to low. So let's say this became unsoldered, and this is just a freestanding wire. It unplugged from there. Okay, electromagnetic radiation in the area could slowly charge up this wire ending enough to send power through the wire and turn this on. And we might not want it on if our battery's already full, for example. So you always want to create a pull-up resistor from the digital output pin to ground with a high resistance, such as 10k ohms, so that things will always default to being off. So we're making sure it's shut off, and no accidental electromagnetic radiation will actually send enough power through to turn that on. Okay, so that's the purpose for that. Now, what had thrown me off before is some other tutorials used a tip 120 transistor, and they put this resistor in series with the GPIO pin leading to the gate of the transistor, which would be correct in that type of setup. Transistors work not by voltage but by current going through them, and the resistor would be used as a current limiter to set the current you want to feed into the tip 120 transistor, which is still wired the same way, but you'd put the resistor here. But for an N-channel Mosfet, you want the resistor to be between the ground and the GPIO output pin, which is the pin leading to the gate of the Mosfet. So that's the only change to my tutorial on N-channel Mosfet as a low side switch. And again, low side meaning on the ground side of your circuit. The high side will be if you placed it on the positive side of the circuit, and we'll go to that next. Okay, so this is a diagram of N-channel Mosfet as a high side switch, and that is our high side switch. Now notice we still start out with the plug, then we have our AC/DC adapter. Let me label positive and negative. Okay, we got our positive and our negative, and positive, negative. Okay, so the positive comes out to the center pin, the drain pin. And then here's our gate pin on the left, which I didn't label. Let me label that real quick. Okay. We've got our gate pin on the left, and trying to let the camera focus here. Yeah, okay. So, our gate's on the left, drain's in the center, source is on the right. Our AC/DC wall wart adapter is going to here, to the center drain pin, and then coming out the source pin. In this case, our N-channel Mosfet is a high side switch, and again we're having a battery as the load, so this is going to charge the battery. This will turn it on and off as a variable resistor. Now, after it comes through here, and this is on or off, and then it comes through the battery and then back to here, that completes the circuit when this is on. When this is off, this doesn't have a completed circuit, so the battery would stop charging. And we would use this, as I said, as a variable resistor to switch on and off the charging of the battery. For example, if the battery was fully charged, it'd be switched to off, and during charging it could be switched on and off quickly in order to have a slower overall current or current limiting factor. The average current would be lower if this is switching on and off every millisecond or whatever, half on during the time and half off during the time, then the current would be cut in half. Okay, so what is all this stuff? Well, basically, with this type of setup, in the example that we're going to be working with, this particular N-channel Mosfet, required a 10 volt gate to source. So you need to put 10 volts on that gate to switch it on. And because the Arduino, which is drawn here, can only output a maximum of 5 volts, it can't turn that on unless if we use another power supply to turn it on. So here we have another power supply. We've got a 10 volt battery or buck converter. It could be between 10 to 20 volts that will turn this on. So basically our Arduino here will switch this low side N-channel MOSFET on, which will mean the positive side of this battery, we'll call it a battery for our example, will come through here and into here at the gate. It will charge up the internal capacitor on this MOSFET, which will switch it on. And then that will come through here and through here and through here. So this is the ground side is being completed when this is on. So that will be turned on when this is on. The wiring for this, the leftmost pin is the gate, center is the drain, and right is the source. The source goes to the ground of the Arduino. The gate goes to a GPIO pin of the Arduino, like that. And then we have a 10k ohm resistor between them, same as we did with our low side switch, 10k ohm resistor between the ground and the GPIO gate controller wire. Okay. And so that this one allows this to be switched on by completing the circuit of its ground side to here. Completes it. And when this is switched to on, because this is on, and the circuit can be completed all the way through, that switches this on. And when this is on, this can work. Now, when you switch this off, then without this circuitry in here, this would just stay on. So we need this as a drain circuitry. Now, so if you imagine all this was gone, this thing would fill up the little capacitor on here when this is switched on. When this is switched off, this little capacitor would stay filled and it'd have nowhere to drain out. And so without this, it couldn't drain out. But because we have this here, supposing we have this on, it will drain out through here, here, and here. So that will empty the capacitor when this is on. If this is off, this will just stay filled. The capacitor will stay filled, and the internal capacitor inside this MOSFET will stay filled, and it will remain on, continuing to charge. So we need to turn this on to open up this line to empty this out. Otherwise, when this turns off, this will just stay on. So, to review, this switch is on, completing the circuit of this power supply to here, filling up the internal capacitor, which switches this on, and then this can run. When this switch is off, this stays on, so when this switches off, we need this to switch on, which will empty out this and turn it off. So we need this to switch on for this to clear out the charge inside the internal capacitor here, and this to go off. So that's the importance of this. This little diode pointing downward is just to prevent this battery from short-circuiting itself. So when this is on, if this weren't here and this happened to be left on, these would both be on. So this would be an open circuit here, and that would short out this battery, and too many amps would flow and it would burn it out very quickly. Or if it were a wall wart or whatever, it would burn it out and the fuse would blow inside it. So that's why we have a diode facing downward, which will not let electrons run up through here. It will only let electrons run down. And so when the electrons leave this internal capacitor inside this high side switch, they'll come through, they'll be allowed through because this allows electrons to flow down, and they'll be allowed to run through and empty this thing out. So that's why this diode's here. It's to protect this thing from going the wrong way if we had both of these on at the same time. But at the start, we'll have this switched to off. This will be off and this will be off. When we want to turn this on, we turn this on, which completes this circuit because this is 10 volts. So that 10 volts will go across the gate to source here, which will switch this on. When we switch this off, this will stay on. And the only way to shut it off will be to switch this on. Once this switches on, the internal capacitor inside here will be able to drain through this drain line. So I call this my drain line. Now, the wiring for this, you can see the far left is the gate, the center's the drain, and the far right is the source. And again, same wiring. We have a GPIO pin from the microcontroller running to the gate of it, which switches it on. And then when we switch that off, then it just automatically shuts off. And then this goes to ground. So we have to share ground coming off the source, the far right pin, which is right here. So we share ground there, like that. So that goes to the ground pin of our Arduino. And between the ground and the GPIO, we have again a 10k ohm resistor, so that if this were to get unplugged, this would still default to being off. So it's just a safety feature. Technically, you could take these two resistors out and it would still work, unless if enough current charged up in one of these to accidentally switch these on. You never want that to happen. So we always put the resistor in, shorting out between the GPIO wire and the ground wire, just as a safety measure. We have one there and there. Those are 10k ohm resistors. So yeah, in this example, we have two low side switches as support circuitry for a high side switch. And again, the high side switch is a switch connecting the positives. It's a floating switch, positive to positive. And the low side switch are all dealing with ground sides of things. Now, after doing that, I realized it looked like maybe we could cut down on some of this wiring and complexity of this support circuitry. So I created another diagram which hopefully will work. I believe it does theoretically, but I would have to test it. I'm not sure 100%, but if you'll follow with me, I believe it will work. And I'll be able to test it out soon when I make a mock-up of this stuff. Okay, so here we have our plug leading to, again, our wall wart. We have our positive and negative. Our positive goes to the drain line of our high side Mosfet. We have our gate line on the left pin, and the right pin is the source. Okay, so this will control on and off of this circuit. And here is our battery we're looking to charge using this 4.2 volt adapter. This is our lithium ion battery. Okay, so it will go like that. When this is on, this will be charging. When this is off, the circuit's broken and this will stop charging. Okay, so now you'll see we have a 10 volt battery, which is enough voltage to turn a 10 volt gate to source MOSFET on and off. Because in this particular use case of a project I'm working on, this has a 10 volt gate to source, and our microcontroller only outputs up to 5 volts, so it would not turn this on without the help of a separate power supply. So here we got a between 10 to 20 volt power supply. It could be a battery, it could be AC adapter, whatever you want. Here's the positive and negative side. It drew it like a battery. So for this example, we'll assume it's a battery. And again, this battery provides the necessary gate to source voltage to switch this on, filling its internal capacitor on. And so our Arduino will turn on our low side switch, completing this circuit. Again, it will go through here, through this, through here, and through to here. So completing that circuit activates this battery, filling the internal capacitor on here. and then when that's filled, then that makes it turn on. So that will be turned on. So when this turns on, this turns on. Now when this turns off, this will stay on because that capacitor is still in there. It needs to be drained out, and it will drain out through here and through this drain line and through to here. This 10k ohm resistor allows the draining to go through, and it's also allowing this battery to short circuit itself. When this is on, this battery is short circuiting itself, but this resistor is a load that prevents this from running too many amps and short circuiting itself to the point of damaging it. Now, the only reason I'm not sure if this will be enough, if this whole setup will work, is because what happens if this battery provides enough current, the 10 volts and enough current, well, set aside the current. It provides 10 volts to turn this on, and then when it's switched off by this, so this thing's no longer activated, we want this capacitor to shut off immediately. And so it will go through here, and it will drain itself. My concern was when this is switched on by this being open, this will send current through here, filling the capacitor, and through here and completing the circuit. But current will also be able to go through here and through here at the same time. So current is going to be passing through the wider circuit, and it's going to be able to pass through here concurrently. And my concern was that maybe the current passing into here, charging up this internal capacitor, switching this on, this capacitor wouldn't stay switched on because it's draining maybe just as fast as it's filling. So it might be like flickering because the cathode side of the capacitor is able to drain out through here maybe just as fast as this is filling it through here. Which is why in our previous example we just had an on-off switch here so that this could be switched off when we want it to be filling up this capacitor here. So will you get away with this? Will this capacitor stay filled up as long as this current is open and this battery is providing? I believe it will, especially with this resistor being where it is. You would think that the discharging through this line would be slowed down quite a bit by this resistor, whereas there's not a resistor in series with this battery going through here. And so that would provide more current to the capacitor in here, resupplying it, than the leaking, the parasitic leak of that capacitor coming through here. So as long as more current can pass into it and keep it charged up, then this will stay on. And then at the same time, the minute this switches off and this is no longer in play, then it will immediately drain through here, and that capacitor will be drained out quickly because it has very low capacity, so it will instantly shut off when this shuts off. So I'm just hoping that it will stay on just from the supply of this, despite the parasitic leak that's happening the whole time when this is giving it electrons to turn that capacitor on. So that remains to be seen. If this wasn't working, then yeah, you should go with just having another switch and then the diode to prevent the backflow prevention, so this doesn't burn out. But in this case, we're using resistors. This won't burn out anyways because it will have resistance to prevent that from sending too much current and burning it out. So this is, I guess we'll call it a maybe, a simplification of this circuitry for a high side switch here supported by low side circuitry. So I'm hoping that we'll just have these two components with the power supply, and that will be enough. And then again, we have our resistor between our ground and our gate controller on here. We have our ground coming off here, coming off the source pin, the far right pin. sharing the ground, and his ground comes off here going to the ground of this, and our Arduino is controlling switching that on and off. And yeah, so I believe this will actually work. So those are our three different examples for N-channel MOSFETs as high-side and low-side switches, and I'm going to be using this for sure as a reference, this YouTube video I'm going to make from this discussion for myself, because it's so easy to forget these concepts and how it all is wired together and how it all works and what everything's for. So hopefully this will help somebody else, and it's definitely going to help me as I sometimes have to review things.